Welcome back. Next up, we're going to talk about embeddings. So embeddings is a little tricky to explain, but I'll tell you the concept up front, and then we'll dive into the OpenAI embedding model next. So the concept of embeddings is basically this idea of having input text, some text concepts that we can essentially convert to numbers. And if we have text concepts converted to numbers, it's very easy to do math with numbers and find related concepts, similar concepts, to build recommendation engines, for example, or to build search engines. So when I say we convert text concepts into numbers, what we're really doing is converting text concepts into vectors. So the embedding model that we'll take a look at in just a moment expects some text input, and it will return a very large vector. So I'm abbreviating it here with the ellipses, the ... It's 1,536 dimensions, I believe, is the number of dimensions for the vector that we'll get back. So you can visualize it as a point in 1,536 dimensional space. And if we have pickled feet that is turned into this vector, and then we have some completely different concept, orange juice, turned into this vector, but then we do this for every single product in a grocery store, as an example, and we have a numeric vector representation of that. Then we can do some math, some relatively basic math, to find clusters or to find similar products, to recommend a product. If someone wants orange juice, what else should we recommend them? If we do some basic vector math, we can pretty reliably get good results. So the whole point of an embedding model is to take text and turn it into these vectors, essentially. And the model that we'll be using is called Text Embedding Ada 002. It returns a 1,536 dimensional vector given a piece of input text. So I'm going to show you some projects with these, but in the next video, we're going to start super simple. I'm going to show you how you get a vector back, how you provide text, get a vector, and that's it. It's not going to do a whole lot for us. Because where the real magic comes in is once you store all of these vectors. If you generate an embedding for every single tweet in a data set or every user product review on your website, then you can store all of that information and then basically perform searches later on once you have that data set of those embeddings. So the first step is to make an embedding. The second step is to build something with those embeddings. So next up, we're going to see how to use Text Embedding Ada 002. In this video, I'll show you how to make a request to OpenAI to use the Text Embedding Ada 002 model to get an embedding for a piece of text. Remember, the operation looks something like this. This is a vast simplification, but we'll give it some concept, a piece of text. It could be a full article. That's actually what we're going to do as our next little project. We'll make an article recommender. Or at least an article search that will give you similar articles based on the whole content of an article. So we'll feed in the content of a news article. We have a data set of them, and we'll get back a vector, a 1,536 dimensional vector. We'll store that, and that's all I'll say about it for now. In this video, I'm going to show you how to make those requests. So just like we have, I'm in a new notebook, by the way, but we have OpenAI completion and chat completion and image and all of that stuff. We have an OpenAI.embedding.create method. And you can also just send a request to the embedding endpoint directly, but we haven't been doing that. We've been using the OpenAI library in Python. It makes it way easier. So we're going to stick to that. So there's two required parameters. The first one is the input piece of text. So let's just do something simple. I don't know. What should we do? Candy canes. Sure. Then we have to specify the model. And the model for embeddings, currently the best model OpenAI provides for embeddings is Text Embedding Ada 002. So Text Embedding Ada 002. And I'll save this to a variable. We'll call it res. So I don't know if I ran these cells earlier just to set up my API key. All right, so we get a response back, and this response is going to look very different than the other responses we've seen so far, because remember, the whole point is to get this 1,536 dimensional vector. It's basically just a list, right, with 1,536 different numbers. It's very long to scroll through, although 1,536 dimensions is actually not very large as far as embeddings go. But if I keep I don't even know if I'll hit the bottom, but if I keep scrolling down, presumably I'll hit the bottom. And that's all that it is. It's a bunch of these numbers, right? These basically directions in 1536 dimensional space in a list. And to actually extract the embedding, it's response and then data and then 0 and then embedding. And that's how we get the actual embedding out. All right. And that's really all there is to making an embedding request. It doesn't seem useful yet, but if you do this enough times on a big data set, on some interesting, every article that we have in a data set, 10,000 different articles, we're doing it on the text of the article. Instead of candy canes, we're doing it on a blog post. And we do that enough times, we'll build up a data set of all of these embeddings that we can store and then refer back to try and find similar articles when we perform some basic vector math. So I'll just show, if I did something else here, instead of candy canes. Actually, before I do that, let me just prove that if I run this same query again, just watch this first value as an example. It's unchanged and we'll get the same vector back. So if I change this, of course, to be some other concept completely, like donkey tail, sure, we get a completely different vector. And that's all that I'll do in this video. Congratulations, we've made our first embedding. The next thing we'll do is build a simple project and hopefully illustrate how this could be useful. Welcome back. So the first thing we'll do with embeddings is a really cool visualization of embeddings in two-dimensional space, basically. So this is a tool called Atlas. There's many ways of plotting our embeddings, but remember what we're doing is taking something in our case, 1536 dimensions and plotting it in two-dimensional space, but still we get some really cool results. So this is a data set of 5,000 movies that I created embeddings for using the plots of the movies. So I'll just show you. We're about to do this in the next video, but this is what the movies look like. Like Phantom Thread, title, origin is American. I focused on American movies just because those are the ones I'm most familiar with. You can easily filter it to be Indian movies, for example. But then there is a plot, and it's cut off here. It's very abbreviated, but the plot can be very long, like multiple paragraphs of text. So I created embeddings for each movie's plot and saved that into a file. And then once I had that for 5,000 different movies, I took those embeddings, which are just numbers, right? Large vectors, and I plotted them using this Atlas tool. So each point on here is a single movie. For example, let's look down here. One of these points, if I can click, is, I don't really know this movie, The Host. Let's try another one. Okay, Vampire in Brooklyn, sure. And what's really cool is that we get these clusters that automatically form, right? This is 1536 dimensional space condensed down with some math into two-dimensional space. And let's take a look at like this cluster right here. I can select in this tool, I can make it a little circle, and I'll zoom in over here. The movies I just selected were X-Men, X2, Fantastic Four, Hulk, X-Men, X-Men Apocalypse, Captain America, X-Men First Class, Logan, Captain America, Spider-Man Homecoming. So yes, X-Men movies, but also generally superhero movies. All were grouped together in there. And I think they're actually all Marvel superhero movies. And remember, all that we did was take the plot of each movie, turn it into this vector using the Embeddings API, which I'm about to do with you. We'll walk through it, and then plot those embeddings. And we get this natural clustering behavior. So I don't know what this group is up here. Let's take a look. Okay, so the movie Radio, which is like a sports drama, The Game of Their Lives, Goal, Fever Pitch, Bad News Bears, Coach Carter, Rebound. So these are all sports-related movies. The Longest Yard. So all of them up top in this cluster are sports-related movies. And again, this is just to help us visualize our data and understand how things are connected. But what we could easily do, and what I'll show you how to do, is using code. So not with this diagram, but using code, somebody could say that they really like this movie, Underworld, Rise of the Lycans. And we can write an algorithm, a very simple one, that finds the nearest neighbors, the closest points in 1536 dimensional space and suggest those as a recommendation. So Underworld Evolution, or Vampire in Brooklyn, or, if this will click, Priest, Queen of the Damned. So these are all like underworld, vampire themed horror thriller movies, Dracula, Twilight. So this natural clumping, this cluster that emerged, I guess you would call like vampire horror, something like that. And it's all, I mean, it's kind of miraculous when you think about what's happening here, right? We're not specifying that it should cluster in any particular way. This is just happening by the content of the plots being turned into numbers and those numbers being plotted. And in the next video, I'll show you how we could go about generating the embeddings, writing a simple script to do it, and then generating this plot. And then following that, I'll show you how we could recommend movies based upon plots. Okay. All right, so let's get started. Remember, our end goal for this video is to get a plot like the one we see here that shows us the general clustering in two-dimensional space of the vectors that we generated using the Embeddings API on a couple thousand movie plots. And it's up to you how many movie plots you want to do, mostly because it can get expensive. These plots are long, so it can be about somewhere between $1 and $2 to do what I did, 5,000 different movies. So you don't have to do 5,000. And you also don't have to do movie plots. It's just a fun example people are familiar with, but you could do something much shorter, small things like, a couple words instead of a paragraph explaining a movie. Anyway, I have a new notebook. I've got my OpenAI package imported, and I have set up the API key. What I'm going to do to start is just get the data set that we're going to work with. So I've put a file in here in my notebook directory that I'm working in called, let's just make a variable called dataset path or something. It's called movie, I think it's just movies or movie plots. I'll have to double check. I think it's movieplots.csv. And then I'm going to read that in using pandas. So I'm just going to do some basic imports. I'll import pandas as PD. If you don't know pandas, well, we're not going to go into much detail, but it helps us work with data. I'm also going to import NumPy while I'm here. And if you don't have either of these installed, you'll want to obviously install them with pip install. Okay, so I'm now going to call pd pandas.readCSV with my dataset path and save that to a variable I'll call df for data frame. Okay. So here's my data frame, right? It's just a little preview of the data frame. It's way too big. I mean, we could generate embeddings for every movie in here, but it would be tens of dollars, 35,000 rows almost. So I'm going to slim this down. As I said in the previous video, what I decided to do was focus on American movies because I was most likely to recognize them. I'm not going to know these Turkish films, and I won't know anything about if they're at all similar or how accurate our embedding clustering is in the recommendations that we generate. So I'm sticking with American, so I'll filter it down to be American movies first using pandas. So I'll select the origin ethnicity, where it's equal to American, and I'll plug that back into the data frame. And now this only gives me American movies, but I still have a ton of them, 17,000 movies. So what I'm going to do is only work with the most recent movies in this data set. It only goes to 2017. Again, I'm not familiar with movies from 1901. So I'm going to sort the results using sort values. And I'll sort the values by release year. Make sure you capitalize this correctly. There's a space, release space year. And then I want to sort them in descending. So I do that by setting ascending to be false. So that sorts them. I get all the 2017 movies up top. And then I'm going to sample 5,000 of them, just as an example here. And I'll save that to a variable. I'll just show you. This is now 5,000 rows of only American movies sorted by the most recent ones. Again, tweak this however you want. If you want old movies, if you want Turkish movies or Indian movies, you can totally do that. You could also do comedies only or horror only. And then I'll save this to a variable. I'll just call this movies. So this is our data set that we're going to work with. I'm going to generate an embedding for every plot in this movie's data frame. And what I need to do is, first of all, set up a function that will generate the embeddings for me. And because this is one of those things that can take a lot of time, things can go wrong. I'm not just going to generate the embeddings and assume they're all going to work at once. I'm going to set up some basic caching. I'm basically going to store the embeddings in a file. That way, if I need them again in the future, which I almost certainly would need them again in the future, that's the point of generating embeddings, I'll be able to access them from the file instead of having to wait to regenerate them, not to mention pay the money to regenerate the embeddings. So that's what I'm going to do next. We're going to set up a function that will generate embeddings for us and store them in a file. Okay. So this is my function that gets an embedding from a piece of text. Get embedding. You pass it a piece of text, you pass it the model, which defaults to text embedding A.2, which is the model we want. One note, it does replace new line characters, which basically, on the docs, I talk about it can negatively affect performance to have those new line characters, so it replaces them with spaces. And there definitely are new lines in the plots that we're trying to create embeddings for because they're long plot summaries and they have paragraphs. And then it calls openai.embedding.create. We pass it our input text, we specify the model, and then we extract the data 0th element, the embedding property. The only thing that's different or new is this @retry decorator. We've seen this before. It comes from a library called Tenacity. So I import retry, wait random exponential, stop after attempt. And this allows me to decorate this function and basically tell it, if this fails at some point, try it again. And it can add in this random wait time so we don't hit rate limit issues. It will attempt it up to 6 times, which is important when we're doing 5,000 or especially more. If we're doing hundreds of thousands of embeddings, we want to keep trying them, and we also want to make sure to avoid rate limit issues. All right, so let's just try get embedding on its own. Get embedding hello world. That will be the piece of text, and I'll just use the default model. And there's our embedding that we get back, right? So it's our 1536 dimensional vector, and that's exactly what we want. This is what we saw in the previous video. It's just wrapped in a function. So the next step here would be basically to call this function on every movie plot in this data frame. However, before we do that, I am going to show you this function that I've written, tweaked basically from the docs, that does some caching. So normally you would actually store your embeddings in some sort of embedding specific or vector data store, but that's out of the scope of this course. So we'll just be doing a very simple example where we store our embeddings in a file, specifically a pickle file. If you're not familiar with pickle, it's a Python standard library that makes it pretty easy to save data to a file and read it back from the file. So the way that this function works is first, well, this is not a function. This part's just looking for some path where I'm telling it you might find already cached results. So movie embeddings.pickle, it doesn't exist yet on my machine. And I'm telling it try to find it and open that file using pickle. If you don't find it, then we are going to just start with an empty cache that will hold our embeddings. Otherwise, we're going to read everything out of that file and use that as our cache. And then this function embedding from string takes a piece of text like a movie plot. It has a model and it has a cache. The default is just this embedding cache right here, which will just be a dictionary. And then it looks to see, all right, is this piece of text, is this in our embedding cache already? So have we already, gotten the plot embedding for the movie Arrival? If we have, then we'll just return the value from our cache. If we don't have that value cached, then we're going to call get embedding for that string. Take that, I'm printing it out just so we can see that it worked. Take that value, and then we are going to add it into our file. So take that embedding that we get back. So basically it just checks to see, all right, we're trying to get the plot for Star Wars. Have we already got this embedding? Is it in this file? If so, return that. If not, go get the embedding using our get embedding function that is right here. Take that huge vector we get back and store that in the file and return it. By the way, what I'm actually using as the key is a tuple of the string and the model. I have to import pickle into this notebook, of course. Let's just do this all up top. import to pickle. It's a standard library, you don't need to install it. And what else is it unhappy about? Ran out of input. Okay, I just changed this file name because apparently I did have a movie embeddings.pickle. So I did moving embeddings demo, movie embeddings demo. Okay, so now if I call my this function right here, embedding from string, and I just give it a piece of text, again, like, well, let's do something else. Chicken is friend. All right, and let's run this. It prints out got embedding just to let me know that it worked. But then also this is what it returned back. But more importantly, it also added this into our cache. So now if I try and get the same embedding, chicken is friend, it's not going to print out that line that says got embedding, because that I should actually change this to say got embedding from OpenAI. If this line runs, it means that we actually made a new request and we got a new embedding using OpenAI and the API. And basically we're charged money. This costs, if we get to this point, we build something. Otherwise, if this is false, that means we already have it in our cache, which is why I'm no longer getting that message. But if I change this to be chicken is friend exclamation point, now it tells us got embedding from, well, I didn't rerun this function, so the text hasn't changed, but it shows us that it did make the request. Anyway, the caching behavior is working. That's what matters. The next step here is we have two choices. We basically want to run the function on all of our plots, but it's probably good to know how much it's going to cost. So what I'm going to do is import tick token, just like that. And now I'm going to isolate our movie plots. So we have our movies data frame. What I want to do is get an array or a list of just the plots. So I'm going to do movies plot. Okay, and then I'll just look at the dot values. All right, so this gives me an array that has all of the movie plots in it. And we could look at the length. It's 5,000 movie plots. And I'll just save this to a variable called movie plots. And then what I'm going to do is use tick token to calculate the cost of generating an embedding for every one of those plots, because there's a lot of text in there. It's a lot. So what I'll do, I guess my cells are kind of out of order. I'll fix this up after I finish recording. But the first thing I have to do is get the correct encoding. So tick token, if you didn't watch the section on tick token, by the way, it's only 2 videos. Go check that out. We have a function called encoding for model, and I'm going to pass through the text embedding ADA 002, and we'll save that to a variable called encoding, ENC. And then I can call enc.encode, and pass it a piece of text, and this returns to me the token identifiers, and then I can calculate the length of each one of those, right? 6 in this case. This would be 6 tokens to embed. All right, but what I actually want to do is do that process for every movie plot in my movie plots. So I'm going to do something like this. For plot in movie plots, I'm going to call encoding.encode of that plot, and that will give me a huge list of the overall tokens, the actual token identifiers, which I don't really care about. I want to know how many tokens are in each one of these plots. And that's still not going to exactly be what I want. This just says in the first plot, there's almost 700 tokens, 757 in the second plot, 974 in the third plot. What I really want to then do is summarize all of the tokens in this whole list. And I'll call this total tokens. And let's take a look at total tokens when it finishes. It's a lot. It is 3.6 million tokens. And then all I have to do is multiply that by the cost. For ADA, it is $0.0004 per 1,000 tokens. And then I'm just going to take this, so 0.0004 divided by 1,000, that's the per token price. and multiply our total tokens by it. And then finally, let's just look at cost. We're looking at $1.4 roughly. And we could probably print this out slightly nicer. Estimated cost, and then we'll round our cost to 2 decimals. There we are. So $1.45 if I'm doing 5,000. Now, if you don't want to run this and pay $1.45, which I don't blame you, you could definitely just cut back on how many plots we're actually generating embeddings for. Try it for 100 to start, or 1,000, or whatever you're comfortable with. So that gives us the cost. We still haven't actually done the generating of the embeddings, which is the next step. So for this next step, all we have left is to call our function embedding from string, this function here that tries to see if we've already got an embedding for that string, or request a new embedding from OpenAI if it doesn't have it. We call that on every single plot in our movie plot list, and I'm just using a list comprehension to do this, to generate a new list that will hold all of our embeddings. So I'm going to call this plot embeddings. And this will take a while. I think I ran this once before, and it was somewhere around half an hour for 5,000. So it's doing the work of going to get our embeddings. You can see it's making a bunch of requests. Everything you see printed out is generated once we get an embedding from OpenAI. Okay, so I'm going to let this finish, and I'll be back when it's done. Okay, so that finished up. I now have this big list called plot embeddings. If we just take a look at one element in there, right, it's this massive vector, but it's not one element long. It should be 5,000 elements long, and it is. So this variable plot embeddings holds 5,000 vectors. Each vector is a 1,536 dimension vector generated from OpenAI's Ada embedding model, 002. So now we have that again, and if I need to run this line again, it happens pretty much instantaneously because we've cached those results. And if I change my data set and I suddenly went to 5,001 movies, it would find 5,000 plots that have been already embedded. We already have the vector for them, and then it would just generate one. All right, so I have that in a file now, and also in this variable. I'm going to stop this video because this is a lot. In the next video, we'll talk about how we can use this Atlas tool to visualize the embeddings, which you don't have to do, but it's just kind of a fun demo. Welcome back. So if you want to follow along and generate your own plot like the one you see here, we're using a tool called Atlas, right? And the whole idea here is that it's taking these embeddings, these very high dimensional vectors, and plotting them, condensing the dimensions down to 2D and plotting them. And it does all of that. So we don't even have to worry about the math to collapse them down. All you do is say, here's the embeddings, and then it handles the rest. So you'll need to sign up for an account. Again, the website the company is called Atlas. I'll include a link to this. You'll need to sign in, but then you'll also need to authenticate. So once you've signed up for an account, you'll install Nomic, N-O-M-I-C, pip install Nomic, not in a notebook, by the way. Do this from a terminal, and then run Nomic login. And then follow the instructions. It's going to ask you to click a link. You'll click the link and copy a token into the terminal. You'll run Nomic login with that token, and then you'll be done. And so that's all there is for that. As far as generating a plot, if we go back to our notebook, we'll need to do a couple of things. So I have this whole list of embeddings. The next thing I'm going to do is import from Nomic. They make some other products. We're going to import Atlas. Atlas is the tool that generates those plots. And the way that this will work is that we'll pass our embeddings through to a function called Atlas and it is called map embeddings. And map embeddings is going to expect us to pass through our embeddings, which we already have, right? It's called plot embeddings. However, it will complain if it's not a NumPy array. So all we need to do is wrap it with np.array. And then after that, I believe we might even be able to just get away with this. I don't know. This is such a simple, there's some other parameters we probably want to add in, but let me just see if this works. It should be able to plot them. it just won't have any other information, right? So my initial example here, when I hover over one of the movies, it has an ID, it has the genre, it has the title, but I'm not providing any of that right here. It looks like it worked. I'm only providing the embeddings. It's still going to plot them. So if you click this link, all right, so it plotted all of my embeddings, but if I click on it, all that it shows me is a random, well, not randomly, but a generated ID that means nothing. So it's working though. We can see that there's these clusters here. What I want to do though is create a new map. So just tweak this, but I want to provide some data. And what I can do when I provide data, it wants me to pass through something in this format. I'll just type it down here. A list full of dictionaries. So I have my movies, the same 5,000 movies, and it's important. They're in these cells, the rows rather, are in the same order as my embeddings array. If they weren't, then we'd have a problem because I need this data to match up with the embeddings. So another option would be to like store the embedding in the data frame itself and make sure that they were staying synced up. But for now, we're doing such a simple example. This is fine. I probably want to pass through the title of the movie, at the very least, the title, and maybe the genre. And this is just for me to look at. Maybe I'll just do title. So all I need to do is extract the title, this row or this column, and get it into this format where we have something like title is set to phantom thread, and then for every movie in our data set. That way it can match up this first element that says title is phantom thread with the first embedding and match the second title with the second embedding. So to get the data in that format, it's pretty simple. Let's do it right up here. We'll access the title from our movies data frame. And you know what, maybe I'll also take the genre just in case. We'll provide the genre as well, just to give ourselves a bit more information. Okay, so this is a data frame. I'm going to turn it into a dictionary using records as the format. There's different ways to turn a data frame into a dictionary, and this is what I want, right? So each row is a dictionary in a big list. Title, phantom thread, genre, drama. And I'll call this just data. Okay, so now I have the embeddings and I have my data. All that I need to do next is pass through this data here. So I'm saying here's the embeddings, and again, the order has to stay in sync. So I can't reorder my data frame. I can't reorder my embeddings. It's a kind of janky, quick solution, but in the real world, we'd probably be using an embedding specific or vector data store, or at the very least, probably putting the embeddings in the data frame along with the actual data in pandas. But anyway, this should work. It will make me a new plot, and this time I'm providing data along with it, not just the embeddings. And I've hit my organizational limit. I ran out of a free number of datums to store, so I had to go delete some of my, I can just show this here. I had to delete some of my projects and slim it down, which is fine. But let's try this again. You shouldn't run into that error. And here it is. Okay, so now each point in here, if I click, you can see has a title, right? It also has a genre. So let's try another one. We'll get out of there. What are you? 23. I don't know that movie. Okay, one more. How about a movie I know? Still don't know Magic Island. Okay, how about this? Deep Impact. I've never seen it. I've heard of it at least. We can also turn on. So I think it's actually still loading. Okay, there we go. I had to refresh the page. It finished loading. Now we're getting some coloring happening in here. And then what's kind of interesting is that I can specify these different coloring topic depths, where basically I believe it's actually not very documented at all, but it appears to be giving me large clusters of color at topic depth of 1. And then if I go all the way down to topic depth 3, the clusters are much smaller and much more specific. Like this, as I think I mentioned, is Marvel, and this is DC movies, DC superheroes specifically. And then, we have, I think is this vampires and werewolves and underworld stuff? And then what's this? Snow White and the Huntsman, Swan Princess, Tangled. So it's sort of fairy tale, children ish. I don't know what you'd call that. Shrek. Yeah, castles, children's movies around fairy tales and fables. We can take a look at what's this outer cluster here. It looks like Rush Hour and Rush Hour 3, Shanghai Nights. So this is probably sort of martial arts influenced movies. And remember, this is not a genre, this is not a tag, this is not something that we told it to set up. This is just the clustering that happens. And this is only with 5,000 movies. Still, really cool, right? You can change this depth and get a different coloring. You can also change the color, actual colors that are used. If you don't like those colors, the Tableau 10 is fine. And that's pretty much it. We got this working. So we generated all those embeddings. We're doing it in sort of a janky way where we're just storing them in a pickle file, which is okay, but not very real world. But the real world solutions take a lot more work. But you store those embeddings once you've generated them, and now we can plot them, or in the next video, we can do some simple, very simple recommendations where you can pass in a movie plot and we'll try and find the nearest matching movie plots based on these embeddings. So that if somebody, let's just pick one of these here, somebody says they really like this movie. I've never heard of that, Amazing Grace. Let's try another one. They really like this movie, Vanity Fair. Okay, I do know that movie. Then we write some basic code that looks to find, the 5 nearest neighbors, basically, but not in 2-dimensional space, rather in 1536 dimensional space. And we might get Sense and Sensibility and The Wings of the Dove, Portrait of a Lady. So these are all, period piece, I think, British romance. I actually have not seen most of those, so I could be completely off base, but I think they're all kind of similar there. So that's the logic that we'll write in the next video. This video is just about visualizing the embeddings. All right, see you in the next one. Well, it's nice to visualize our embeddings like this, to see them. It's not even just nice, it can be useful to understand your data. The next step that I want to show you is how to do some basic recommendations. So how do we say to somebody who likes the movie, Lassie, which if you're not familiar, it's a dog movie. How do I write code to basically recommend the nearest other movies in 1536 dimensional space? So what is this here? Oh gosh, my dog Skip. I don't know if I've ever cried so much. This movie as a kid absolutely ruined me. We saw it in theaters. So it's a good recommendation. It's another dog movie. Far From Home, good dog. So these are all like dog movies. Yeah, Best in Show, Good Boy. So what we're going to do in this video is write a function that it has nothing to do with the 2-dimensional space you see here. This is just to visualize it. It will work with our vectors, our embeddings that we've gotten back. We have them in a file. And what we'll do is we're going to work with plots only. So somebody, me, will pick a movie plot. We'll write a function that takes that movie plot. It turns it into an embedding. And then it compares that embedding to the existing embeddings of every other movie plot. And it does the math to see which ones are closest. So in the real world, a much better way of doing this would be to have somebody enter a movie title, take the movie title, find the corresponding plot, turn that plot into an embedding, use that to find matches, and then take the matching plots that we get back and get the title from those plots. But that's a bit more work. It's not hard. It just means reorganizing our code. So we're going to do a very simple version. Essentially, we're going to write a function. I'll start it now. Print recommendations from strings. And this function we'll expect a couple of parameters. I'll do this on multiple lines. So the first thing is going to be a list of strings. These will be all of, in our case, movie plots. And then we're going to specify index of source string. So the way that we'll call this is we'll pass all the movie plots in, and then we'll pass an index of the string that we're interested in, the plot that we're interested in. And then what we're going to do is specify how many nearest neighbors we want to find. So the equation that's used here is called KNN, or K nearest neighbors. So we'll call our parameter K nearest neighbors. How many results do we want? Let's have it default to 3. So you could specify you only want one match, but maybe you want 5. And those will be our parameters. Okay. And I guess, you know what, I'll add in the model too, which will default to text embedding ADA 002. Make sure I add a comma as well. All right. So our basic steps look like this. I'm going to write some comments. We're going to get all of the embeddings that we already have stored. Then we're going to get embedding for our specific query string. Then we're going to get distances between our embedding and all other embeddings. Okay, and so that's the hard part, but there's functions that we're going to use from OpenAI. We won't be writing that. And then once we have those distances, we'll get the indices of the nearest neighbors using those distances. Okay, so let me indent this all properly into our function body. The first step is to get all of our embeddings. And normally, like I've said already, we would put them in some sort of embedding or vector-specific data store. For now, we're not doing that. We have them, we have a function that loads them, right? Embedding from string. We already have that function pre-written right there, and it looks to get the cached versions of our embeddings if it can find them. So I'm going to call it for every string in whatever strings were passed. So we'll pass in a whole set of movie plots, but this is more general purpose, right? It's not using the word plot because I want it to also work for whatever, news articles or product reviews. So it's just any generic list of strings. So that goes and loads all of our embeddings. And if needed, it would make the embedding calls if we didn't already have them cached, but I already have them cached. Then we're going to go into that embeddings list and access the specific embedding at the index that a user provided. So again, we're just going to pass a number like the 7th movie plot. So we get all of the embeddings, and then we get specifically the 7th one, if that's what our index is, and I'll call this something like query embedding. So now we have all embeddings, and then we have the one target embedding. Let's say that's the Lassie embedding, the plot of Lassie turned into an embedding. Then we have to calculate distances between those things. And the way that we do that, you could write a function to do it yourself, but OpenAI has some utility functions. I'll just show them to you. In embeddings utils in the OpenAI package, we have a couple of utility functions, including, keep going down, where are you? We have distances from embeddings. And this expects us to pass in our query embedding and a list of embeddings, and it returns a list of all the distances between a query embedding and a list of embeddings. And there's different metrics that we can use. The standard one is to use cosine. It performs something called cosine similarity. So that's the default distance metric. You can pass your own in. So we need to import distances from embeddings. That's the next step. So from OpenAI dot, I think it's embeddings utils, import distances from embeddings. Okay, so that will give us this function that we can then call in here. And we'll call distances from embeddings. And we specify first our target query embedding. Then we specify all the embeddings. And that will hopefully give us a big list of distances. So I'll save that to a variable. And make sure I fix my indentation here. Okay, so once we have that, what I can do to start, I could just print distances. It's going to be a lot to look at, but I just want you to see what happens. So I'm going to call print recommendation from strings. Now, remember my movies is ordered by release year at the moment. So the first embedding, if I passed in index of 0, it'd be this one. Let's see. Let's do index of 0. So Phantom Thread. If you've ever seen it, it's a pretty good movie if you like Paul Thomas Anderson. So I'm going to pass in all of my movie plots as the list of strings. So I have a variable called movie plot still from the previous video, and then I'll pass my index of 0, which is the plot for Phantom Thread. We're not going to get any results yet. What we will get is a big list of distances. Notice, of course, the distance for this first point is 0 because that's the embedding, that's our target embedding. So of course there is no distance there, they're the same vector. But then for every other one, right, we get a different distance. And now what we need to do is basically go through this list and figure out which ones are closest, right? And you could write a function to do that yourself. It's not terribly difficult, but there's also a helper function that we get called indices of nearest neighbors coming from the embedding utils. So I'm going to add that on. Indices of nearest neighbors from distances. Okay. So then I'm going to call that. Indices of nearest neighbors from distances expects a list of distances. And then I'll save that to a variable called indices. Is that how you spell indices? Indices, there we go. Of nearest neighbors equals that. And why don't I just print that? So you can see that there. So I'll do the same thing. But now what it gives me back is a list of indices. So of course, the element at index 0 is the closest because remember, that's the target embedding anyway. So then the next closest one is at index of 1535. The one after that is at 3418. That's the index of that embedding. Okay, so then what we'll do is basically iterate over this list. If we're looking to get the 3 nearest matches, we'll iterate over it. We can't do it necessarily 3 times because we might match the exact original embedding. So we need to iterate over it some number of times and keep track of how many nearest neighbors we found. And if we find 3, then we're done. If we find 5, if that's what this number is passed in as, then we're done. So we need a loop here. Again, it's not as simple as just saying take the first 3 or the first 5 because we have to ignore the original query embedding that matches, this is the plot of, what was the movie? Not Lassie. This is the plot of Phantom Thread. Okay, so I'm going to do a loop. For I in all of our indices of nearest neighbors, I'm going to, I guess I'll take the plot itself. So how do we get the plot? If we have, when I say plot, I'm referring to, the movie plot, not the graph or something. So we have this list of movie plots that's passed in, or a list of strings, in our case movie plots, and I have the index of the one that we're searching using. So what I do to find the actual element at that location, very simple, strings at this index. So I'm going to call this query string equals whatever is in the strings list at our index of source string. So this will hold a movie plot. And then all I'm going to do is check to see for each one of these indexes in the nearest neighbors list that was generated for us by OpenAI, if the query string is exactly equal to whatever is located at the strings list at that index, that means we want to continue, meaning just go on to the next iteration of the loop because we found the original plot. We don't want our match to be the same plot that we passed in. So once that's happened at some point, the other thing to consider is, okay, we need to get 3 and no more than 3 of these indexes. Or we need to get 5, no more than 5, but exactly 5. So we need some sort of counter. So I'm going to call this matches maybe. Match counter, match count will start at 0. And then I'm just going to write a little conditional if match count is greater than or equal to our number of nearest neighbors, k nearest neighbors. We're going to break out of the loop and be done. And then otherwise, that means we found a match. We're going to increment it by 1. So walk through this. We start with no matches found. And we loop over this list that has all of the indexes of the nearest neighbors in order. This is the closest match. That's the index of the closest match. This is the index of the second closest, the third closest. And then we check to see, all right, are we looking at the actual same element, the same plot, the same string? If so, move on, go to the next iteration of the loop. Have we found enough matches already? If so, we're done with the loop entirely. Otherwise, that means we have a match. We'll increment it by 1, and then we'll print out our match. So to print out the match, basically all we need to do is take strings and use the index coming from this list. And maybe we'll add a little print statement above it. Print, found. Let's do an F string. Found F closest match. Okay, and then on the next line, we'll print the plot. Well, we'll print whatever is in the strings list, strings of I. And then to print out the distance, we have our distances list from up here. And we'll do distances of I. Okay, so let's see how this works. Remember, this is for phantom thread, which I don't know, a lot of you probably are not super familiar with. Maybe let's do index of 2. So this is 0, 1, 2. This is Alien Covenant. I have not seen that movie, but I have seen other Alien movies, the Alien 1, Alien 2. Okay, so let's try running this. And F is not defined. Oh, what did I do in my F string? Oh, geez, what am I doing there? Found. What I meant to do there is the match number. Let's just do match count. Okay, found one closest match. Here's the distance, and then here's the plot. Now, I don't know what movie this is. Archaeologists, Elizabeth Shaw and Charlie Holloway discover a map, star map, spacecraft, Prometheus. I assume this is Prometheus because it says Prometheus in there. So if we scroll down, and then we got our second match somewhere further down. I mean, you can see how long these plots are, by the way. Right here. No, that's the third closest match. Where's the second one? Right here. So again, we don't know what movie this is. Predator, some variation of Predator. That seems like a good guess. It's, closely tied to Alien versus Predator and all that. And then further down, we've got another one. Unmanned Pilgrim 7 space probe. I don't know what movie that is, but some sci-fi space movie. So of course, the problem we have right now, as far as implementing this in the real world, is that we're searching by plot and we're returning the plot. What you would really want to do in the real world is have someone pass in a title to the function, like Lassie, and then have it return the nearest matching titles of those matching plots, if that makes sense. So we still are using embeddings on the movie plots because that has the most information in it. And that's what I want to know is like what movie has the most similar plot. But we probably want the movie title because just getting the plot is, you can look it up and easily figure out with a Google search what movie this is, but it's still kind of clunky. So I'm not going to do it just for the sake of time, but basically you would write a function. You could write this function to expect a title, look up the plot of that movie in our data frame, embed the plot, do the same comparisons we're already doing. Then you get the matching plots, 3 matching plots or 5 matching plots or 1 matching plot that's closest to your search. Then take that plot and find the title of that movie that has that plot. But it is indeed working, even if it's just a little clunky. This is more of a demonstration anyway. And remember, what makes it all work are these helper functions. Distances from embeddings, that's the most important one. This takes our massive, 1536 dimension vectors, and it calculates distances between them, returns a list of those distances, and then this helper function, this one would be easier to write. It basically just gives us a sorted list of those indexes based upon the distances that were calculated. Next up, we're going to look at another way of using embeddings, basically to enhance GPT. To enhance the question answering ability of, let's say, GPT-4 about topics that it wasn't trained on. So imagine that we run a company, let's say a car company, and our car company has 5 different cars, and each car has a huge instruction manual and a whole, database of part numbers and, lists and information that GPT-4 just doesn't even know about. But what I want to do is build some sort of Q&A assistant that can help my customers who are troubleshooting their cars. So they might ask something like, what is the part number of the bolt holding the hitch on a ZF345, which is not a real car. We don't have a real car company, but just imagine, any company that has their own products, their own internal data that they want to train a model on, or at least be able to ask questions to GPT about. GPT won't know a thing about this information. It doesn't even exist. But even if it did, unless it was on the internet before September of 2021, GPT-4 won't know about it. So what we can do to make basically an enhanced version of GPT-4 is use embeddings. So in the case of our fictional car company, we could take all of our parts lists, all of our internal information, all of the instruction manuals for the cars and for how to service the cars, and we turn them into embeddings. So we'll have to split them up, and they're very big manuals. We'll split them into small pieces. We'll generate our vectors and store them in a database, just like we did with movies. But then this is the new piece. If we're building an assistant, some sort of virtual chatbot thing, when a user asks a question, like this question right here, what is the part number of the bolt holding the hitch on a ZF345? What we'll do is turn that into an embedding too. So we'll have the question as an embedding, and then just like we saw in the previous video, we can compare that embedding to other embeddings and find the nearest matches. Use the nearest neighbor algorithm to find the closest matching embeddings. And when we've done that, that will hopefully give us the relevant information to answer that question. So it would probably give us, again, this is all hypothetical, information about ZF345's hitch, and maybe another embedding that was the result of embedding the part numbers for ZF345, something about bolts. So we'll go and gather, let's say, 5 different embeddings that match. They're the closest matches to the embedding of the question. Then we take the underlying text that generated those embeddings and we stick those in the prompt to GPT-4 as part of the context that we provide. We'll say, here's some context to help you answer a question. And then we finally throw in the user's question at the end that says, what is the part number of the bolt holding the hitch on a ZF345? So it will look like, hopefully if it all works well, it will look like GPT-4 knows about or was trained on our data. But in reality, it knows nothing about our information unless we provide it in the prompt. So I have an example of this. I wanted to do this with instruction manuals. My inspiration was I have a very complicated generator at my house that is always breaking, and I'm always trying to avoid calling the people to come out here because it takes them forever and it's very expensive. So I'm reading the manuals. There's like 3 or 4 different manuals I have to cross-reference, and they're long, like 200 pages each. I wanted to use those or some sort of instruction manual found online and turn it into embeddings and make a very specific chatbot that could help us with my generator or with your car. But those are all copyrighted. I couldn't find any licensed, Creative Commons licensed manuals that we could use. So instead of that, I'm going to show you a different example. I'm going to use Formula 1 data from 2022, which GPT-4 knows nothing about because its training cutoff was September of 2021. So if I try and ask it a question, this is just with ChatGPT here, who won the 2022 Monaco Grand Prix? I guess I should say the F1 2022 Monaco Grand Prix. It's going to tell me I can't answer that. My training data doesn't have that in it. I cannot provide real-time information or information beyond my cutoff of September 2021. So it can't answer anything about F1 after its training cutoff. Now, if I said who won the 2021 Grand Prix, it could tell me that, but not 2022. So now let me show you my enhanced version where I am using this strategy that I've laid out here. I created a bunch of embeddings about Formula 1 2022 races and the results. I store those in a database, and then a user can ask something like this question right here. Let's do Monaco. Who won the 2022 Monaco F1 Grand Prix? And we'll talk about what it's doing. None of this is the output. This is just some debugging stuff. But then at the very bottom, it says Perez won the 2022 Monaco Grand Prix, and that's correct. Sergio Perez did win. Here's another example. What happened in the first lap of the 2022 British Grand Prix? There was a big crash. GPT-4 knows nothing about it, but this function, my enhanced version, knows about it because I'm providing the context when I'm asking the question. So I'm not training the model in any way. I'm just doing some fancy extra steps to provide context when a user asks a question like, what happened in the first lap? Well, it tells me now a multi-car crash occurred on the opening lap of the 2022 British Grand Prix, blah, 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 blah. It's kind of a crazy crash. So it's not quite as exciting or as useful. I wouldn't say part numbers is exciting, but this is a more real-world application, taking instruction manuals, taking product data that you have, taking customer data, anything that GPT-4 doesn't know about, using that information so that it seems like it knows about that using embeddings. And unfortunately, I couldn't find company data that we could use that had the correct license. So we're using F1 data, which still shows it still works, right? It's answering questions that it can't answer otherwise. Just imagine instead of F1 data from last year, 2022 season, instead of that, imagine that we're using, company data, information about a particular user that our chatbot is talking to. If we're some big company, let's say Bank of America, and they want to build a chatbot that will be able to talk to me about my accounts there, and my history and all that stuff, they could create embeddings with all of my data and every other user that uses Bank of America, and their chatbot could know that information and talk to me about it. So that's the game plan here. We're going to take F1 data from Wikipedia from the 2022 season that GPT-4 does not know about. We're going to generate some embeddings using that data, store them. Then, when I ask a question like who won the British Grand Prix in 2022, we turn that question into an embedding, and then we compare that embedding to our existing embeddings in our database. And then we take, let's say, the 5 closest matches using some math. And then we take the text from those embeddings, the text that generated those embeddings, we stick them in the prompt, then we ask the question, who won the British Grand Prix? Then we send that off to GPT-4, and it has additional context and hopefully can answer our question. So in the next video, I'll walk you through the code. We're not going to do it from scratch because there's a little bit going on. There's some utility functions. It's just more complicated than what we've done so far, but that's the basic concept. And it's a fun use case that's pretty useful. So I'll show you how it works in the next video. Welcome back. So in this video, I'm going to show you the working version of this F1 question and answer assistant that is aware of, I'm using air quotes here because it's not aware of the 2022 season, but it will behave like it is because of our embeddings and some legwork we do before we actually send a prompt off to GPT-4 or 3.5. So again, I'm not going to type this from scratch, but I'll walk through how it works. The first thing I'll talk about is just how I'm getting the F1 data. So there's a page on Wikipedia for every race in each season. So here's the 2022 Monaco Grand Prix webpage on Wikipedia. And there's one for every other race of the calendar year. Okay? So what I have here is a list, a CSV file, which honestly I could have just done a regular Python list. It's not that long, but a CSV file with the name of every Wikipedia page for each Grand Prix in 2022. What I'll do is do some scraping. I'm going to send our JSON request to wikipedia.whatever/this, and then Wikipedia whatever/this, and I'll download the page contents, and I'm going to stick that in a data frame. So that's the first bit. And I'll just show that happening. Let me go back to this. Now I have everything cached, but here's when I read in my CSV file. Okay, so I'm just getting the names of the pages. And then this function is called Wikipedia API fetch. Nothing to do with GPT or OpenAI. It simply takes this base URL, it throws on the article title, like 2022 Australian Grand Prix, puts that in there, and then sends a JSON request. And it gets back some information. We just make sure that we get the information back. It's not an invalid URL. We get back JSON, we take that text, and I'm adding it to our data frame. So let me just show you, after I run this, it's all cached because it just takes some time to make these requests. So I'm using this memoize to SQLite decorator function that I wrote. This is very similar to some of the other memoize decorators you've seen. All that it does is it stores the results in a cache SQLite file. So it's just storing them so that, if I run this again, it's running right here. It's not having to make requests over and over and over and just, take time and potentially get rate limited by Wikipedia. Instead, it just uses the cache results found in our SQLite database. This is the part that's actually calling it. So for every link in my data frame, remember, these are the links, I am applying this function Wikipedia API fetch. And let me show you down here. If we just take a look at our data frame, this is now what it looks like. So before I did all the fetching, this is what it looked like. Now, after I fetched the Wikipedia information, we have page content, and then I also went and fetched the actual page title in case it differed from the URL. So page content here, if we just look at one of them, is quite long. Let's do page content, page underscore content. of, let's just take the first, let's do index of 1 here, the Abu Dhabi Grand Prix. This is the whole page content. So it's pretty long. This is all the text that we got back. And we could theoretically just try and embed this, turn this whole thing into an embedding. But there's 2 problems. One, it could be too much content to make into a single embedding. But additionally, there's probably a lot of topics and information in here that there's no need to group them all together into a single embedding. Smaller embeddings generally will work better because we're going to take this text eventually and stick it in the prompt to GPT-4. So if we're throwing a whole article in there, that doesn't necessarily leave us many tokens for the question and for the response. So there's a middle ground. We don't want to turn like this into an embedding and this into an embedding, but we'll try and divide this into logical pieces. And if you see these double equal signs, this is how in the JSON that we get back from Wikipedia, this is basically distinguishing one section from another. So this is the background section, and then we have some other section here and another section, the entrance section. So this is a place that probably makes sense to split some of our data up. And that's exactly what I do with this next bit. So once we have these huge summaries or these huge Wikipedia articles, we fetched them, they put them in our data frame. I do some fancy work to split them. So I wrote a generator called Wikipedia Splitter. It takes each page content, so one of these big strings like this one here, that whole thing about which Grand Prix is this? I already forgot. The Abu Dhabi Grand Prix. And that's actually a short one. Some of the others have much longer pages, like the British Grand Prix. If there's any notable events at that race, the pages are quite long. So we take that page content, and then I tell it basically the largest amount of tokens that we're allowed, which depends on the context window for each one of the models. If we're using GPT-4, it's 8,000 something. If we're using 3.5 Turbo, it's 4,000 something. So I wrote the function in a way that it's flexible depending on your max context window size. And then I provide this list of regular expressions where I think it should try and split. So instead of just picking the first, 2,000 tokens, wherever that happens to be, I wanted to try and split into the individual chunks, right? Like this could be an embedding. This could be an embedding. This could be an embedding, and so on. And the way that I did that is by using regular expressions to look for the section dividers. In worst case, I'm telling it to look for a new line character. So this Wikipedia splitter, we can look at it. It's kind of a lot. It's in this file called F1 utilities. Here it is. It's a generator function. There's a lot going on, but it tries to split a big piece of text from Wikipedia into smaller pieces that make sense to turn into embeddings. You can totally look at this code. I'm happy with it. I'm spent a lot of time writing this, but I don't want to spend a lot of time explaining it because it also has nothing to do with OpenAI. It's more just turning a big piece of text into small pieces and trying to figure out, well, how small do we want to make them or how big can they be given the limitations of the number of tokens that we have in a given context window for each model. Okay, so this is going to return. We go back here. We have this generator that we can iterate over. For each section that we get back, I'm appending the sections to a list that I'm calling sections. So after I run this, you'll see I get some output saying, here, okay, this section is too long, so it split it. This other section is too long, so we split it. Too long, too long, too long, and so on. It keeps splitting it. And then if we look at what we get back, it's this list of small sections. And I made a data class called section. Let's see if I can try and show you one section here. Right there. This is one section that it split. And then here's another section that it splits for that same race. So we get this big list of pieces that are of the appropriate size to then turn into embeddings. But they're not embeddings yet. Okay, so then we get to this piece here. This is just about cost estimation, where I'm telling it, all right, we're using the ADA002 embedding model, and I get the correct encoding. We already saw this previously to estimate costs with embeddings. And then I take all of the sections that we just got from our splitting of all of the text. So we take all those sections from all of the races, and we pass them into the embedding.encode, and then we count how many tokens we got back, we sum them up, and then we multiply by the cost per 1,000 tokens, or the cost per token. And then if I scroll, what am I printing? I think I need to scroll all the way down here. There it is, estimated cost of 2 cents. So it's not that much text because it's only, 20 races or something to actually perform the embeddings. Okay, the next step is to generate the embeddings, which I've already done for the sake of time, and I've cached them as well. I've written this function getEmbedding. So what I'm doing is calling it for every section in our sections list. Let's look at getEmbedding. It is in my utilities file. So I have F1 utilities and then just utilities, because I wanted to separate out what was specific to this F1 project versus what you could reuse. So for example, this, keep going down here, getEmbedding is a generally useful function. This is very similar to our getEmbedding from earlier. All that it does is it takes a piece of text, replaces new line characters with spaces because of performance issues with generating embeddings. And then we generate the embedding with text ADA 002, right? We tell it, here's your piece of text. We get the embedding back and we return it. It's decorated with this retry decorator to make sure we avoid rate limit issues. And if it fails, it tries it multiple times. And my memoized to SQLite function, which I'm not going to walk through. It's honestly been a very useful decorator that I wrote for this course. It just takes whatever the return value is from this function and will store it in a SQLite database. So I'm using SQLite this time instead of using Pickle, just to show you another example of how you could store these embeddings. But remember, the real way of doing this is a bit more complex. There are vector-specific data stores. So I store that in a SQL database. That's what this function does. You can see the function right here. We won't walk through it, but it stores information in a SQL database and whenever it's used to decorate a function. So this means that if I go back to my notebook here, I've already generated these embeddings, and if I run it again, it finds the cached results. Now, if you want to do this yourself, you run this, presumably if you try it on new data and you don't have the embeddings cached, it's going to go and get an embedding from OpenAI for each one of our pieces of text. Each section is what I'm calling it. Okay, then we have this list of embeddings, or it's actually this dictionary of embeddings here. So we're done with this first piece. Generate a bunch of embeddings and store them based on our own specific data set. Again, it'd be way better if this was like company-specific data, but we're just using F1 data from 2022. We have the embeddings now. I have a whole, I guess I should just show you that. If you want to look at the dictionary, let's just look at, well, if I try and print the whole thing out, it's not going to be very happy with me here. But there it is. We have the section as the key. All of this is the key, and then we have the corresponding value, this massive embedding, 1536 dimensional vector, and this is all for this first one. And this is where, you would use a vector-specific data store to help you. Oh my gosh, a lot of scrolling. And then we get to our second section here, and its corresponding embedding. And then we repeat that for however many hundreds of embeddings I have. It's a pretty small data set I'm working with, and that's another reason I chose F1. It's cheap. It doesn't cost multiple dollars to generate the embeddings. In the next video, we'll wrap things up, and I'll show you how we can actually do the question and answer portion. All right, so next we move on to the final piece here of creating this Formula One 2022 season Q&A bot. We have the embeddings generated from all of the Wikipedia data about the races. We've stored them. Now, what we need to do is write the code that takes a user's question, like who won Monaco 2022, turns that into an embedding, compare that embedding to all of our embeddings that we already have, pull out the matching 5, 10, however many, 3 little sections of content that correspond, that were the close matches, put those in a prompt, and then send that prompt off with the question to GPT 3.5, Turbo, or GPT-4. All right, so the first thing I'll show you, very simple, a function called getMessages. This simply returns the initial set of messages, very simple. So it has things like the initial prompt, the system prompt. You will receive a question from the user and some context to help you answer the question. Evaluate the context and provide an answer if you can confidently answer the question. If you're unable to provide a confident response, kindly state that it is the case and explain the reason. Prioritize offering an I don't know response over conveying potentially false information. The user will only see your response and not the context you provided, so please respond in precise detail, directly repeating the information that you're referencing from the context. So that's the initial system directive. Then we have a second message. This is a user role. Using the following information as context, I'd like you to answer a question. And then we're going to put the context that we pull out using embeddings, which will be passed in to this function. And then finally, please answer the following question, and the question is also provided as an argument to this function. All right, so that's get messages. But then the real thing that makes this all work, that actually makes our request, is this function right here, ask embedding store. It expects a question, it expects a list of embeddings, and then a number that specifies the max number of documents that we want to search for. So you can include more context if you want, but then the problem is you take up more space in the prompt. So you could do 3, 5, 10, it's up to you. Okay, and then in here, the first step, just like I said here, is take the user's question and turn it into an embedding. That's what we do right here. Get embedding of the user's question. And then we perform the get n nearest neighbors search. This is a function also defined in utilities. Get n nearest neighbors. And I'm not going to go over this in too much detail, but I put some notes in here also to explain how it works, and also that you're going to be much better off if you use a vector database in general, something like Pinecone. But what we do is we take the target embedding that you provide, so whatever the question embedding was, and then we generate a whole list of distances, similarities between the target embedding and all of the embeddings that have been provided. And we do this using cosine similarity. This returns a list of distances, and then we sort them and basically find the closest matches. We return the nearest neighbors. This is not the most efficient way of doing this, by the way, but it's about the simplest to understand and walk through. So I'm hoping you could walk through this code and get an understanding of how it works. And we also could have used some of the functions from the OpenAI embedding utils, which we did previously. I just wanted to show another approach here where the code is a bit more exposed. Okay, so this whole function takes in a query embedding and then a whole list of embeddings, and it returns n nearest neighbors. And n is going to be passed in. Are we trying to find the 3 nearest matches, the 5 nearest matches? It's up to you. So then once we get that back, then there's this chunk of logic in the middle that I'm kind of going to just ignore. I'll briefly tell you what it does. There's a chance that, let's say we have a 4,000 token context window and somebody asks to get 10 documents. So if you pass in 10 as the maximum documents, we get 10 nearest neighbors for some question embedding. We might not be able to fit all 10 of them in the prompt. So this math does some math to figure out, okay, how many messages can we fit? And then we use that number to fit the most possible messages into our context list. So this context list will be as many possible related Wikipedia snippets that will fit within our prompt token limit. So that's what this logic does in here. So once we get a list of, let's say, 5 nearest neighboring pieces of text, Wikipedia articles, let's say about the British Grand Prix or something, pieces from that article, there's 5 of them. If they all fit, if we can fit them into the prompt, then we're going to take them and stick them in this context variable. We take that context variable, and then we're going to pass that through to the get messages function I just showed you that takes a list of context and a question. And then that generates a prompt, and we take that prompt and we call openai.chatCompletion.create. So just to refresh your memory, right down here, this function we saw at the beginning of this video, expects, it's called get messages. It expects a context piece of text and a question. And technically what we're doing is taking the list of context and turning it into a string and then putting that string into the message. And then we take the user's question, like who won the British Grand Prix, and we put that in there as the last thing. So this returns this list of messages. And then we make the API call. Where are you? Right here. Using openai.chatCompletion.create. You specify the model, specify the messages, and then we return whatever that content is that we get back. And I'm going to turn off my print statements for now. And I'm going to do that because if you remember the first time I ran this to show you that it worked, like this example, what happened in the first lap of the 2022 British Grand Prix, this is the actual output that we got back. All of this is showing you the prompt. This is the big prompt that we sent. So all this stuff. And I want to be clear, this is kind of a crude approach, having such big pieces of text just thrown in the prompt, but it does work. It provides the context, right? So we can see this is information. It looks like it grabbed stuff about the French Grand Prix, no idea why, but it also grabbed a lot of information about the British Grand Prix, and that was needed for GPT-4. I think I'm actually using 3.5 Turbo to save money. It was needed for GPT whatever model to answer a question about information it was never trained on. So let's try one more. Well, let me just run it to show you it does in fact work. And there we go. It says a multi-car crash occurred in the opening lap of the 2022 British Grand Prix. And you can see, it works. That's correct. That's the answer I was expecting. Let's try one more. We could try something like, who finished 9th in the French Grand Prix in 2022? And it says Daniel Ricciardo did. Let's verify. Okay, this is the Wikipedia page for it. Let's look. This is qualifying results. It's not what we want. Here's the race classification. 9th was, in fact, Daniel Ricciardo. All right. And let's try another example that is not race specific. So something like, who won the F1 Drivers' Championship in 2022? So GPT-4 on its own won't know that. But let's see. Okay, it got it. Max Verstappen won the F1 Drivers' Championship in 2022. By the way, I'm passing 10 documents through as the maximum. We could try adjusting this. The risk is if you just provide one, that it's not going to be accurate enough. If you do 2, 3, 4, somewhere in here, let's do 5. It probably will still work just fine. Yep, Max Verstappen won the F1 Drivers' Championship in 2022. Pretty cool. I think it's a fun little demonstration, and I know I'm a broken record on this, but imagine instead of using F1 data from Wikipedia, you have real legitimate customer data, private, manuals for your company, whatever information you would want a chatbot to know about that it does not know about natively. It was not trained on. So that might be recent sports data, sure, but in all likelihood, it's something specific to your company or your project. But we can make an assistant, which, right now we could easily turn this into like a chatbot, make a little UI for it and build a front end in the browser, for example. And you could do a big project using this. I'm just showing you, with a simple function that we execute, the logic works. So I think it's a pretty nifty use case for embeddings. And that's it. I hope you enjoyed it, even if you don't care about F1. Welcome back. So in the next couple of videos, I'm going to walk through a small project I put together that involves scraping or collecting a bunch of Reddit comments from the Reddit API, saving them, and then sending those comments to OpenAI. We're using GPT 3.5 Turbo to save some money, and classifying their sentiment. And the end result eventually is that we'll basically have a plot of sentiment for certain subreddits. And the data set I chose to work with is cities. So each city has a subreddit. I'm just using American cities, New York City, Seattle, LA, that sort of thing. And then eventually we end up with, all the way down here, a plot showing the sentiment of the comments on a given subreddit. Now, I'm not saying this is the most accurate thing on earth. It's just a simple demo. Although it is interesting, we can see on our plot the most negative sentiment is concentrated in Orlando. And recently in Orlando, so I chose to go with recent comments from each subreddit from recent posts. And in Orlando recently, there's been a whole bunch of drama between Disney and Ron DeSantis' administration and all sorts of negativity around Disney trying to basically fight off the government, or depending on whose side you take, the government trying to rein in Disney. Anyway, so I'm not surprised to see Orlando have such a high concentration of negative comments. What is interesting is, other cities I would have expected to have a lot of negativity based on my experience browsing the San Francisco subreddit. I thought there'd be more negative comment sentiment. It seems to be actually one of the most neutral heavy. If we're on a scale from negative 1.5 to 1.5, it's really a scale from 1 to negative 1 to 1. The plot just adds in some extra space on the left and the right. So it's really from negative 1 to 1. San Francisco has a pretty heavy concentration of neutral sentiment. And then Washington, D.C. has a lot of very positive sentiment. Again, I'm not drawing any conclusions from this, although I do think, you can definitely look at, sadly, also Nashville recently had a school shooting. So there's some negativity there. But on the other side of things, maybe I'm just sort of looking for that in the data, because I have no idea why Austin has a lot of negativity and Columbus and Seattle. I might think Seattle, has all sorts of drama with city politics, and their subreddit has lots of posts about crime and homelessness and drug use. But San Francisco over here, I can tell you firsthand, there's a lot of comments too about drugs and crime and homelessness, but it doesn't seem like they're as negative. So not trying to draw conclusions. I just want to show you the project. And there are different data sets we could try running this on too. If I go back, I'll show you the original data set. It's just cities, but I commented out some other examples: iPhone versus Android subreddits, the Star Trek versus Star Wars subreddits, different English Premier League teams and their subreddits. And so there's some interesting variations there that we can try. All right, so the way that this will work, I'm going to walk through it in the coming videos, is that we start by scraping or by downloading a bunch of comments from Reddit, which is what happens right here. We use the Reddit API. There's a tool, there's a package called PRAW, P-R-A-W. I think it stands for, what is it? Python, have I lost it? Here it is. Python Reddit API wrapper, I believe is what it is. Anyway, so we'll talk about signing up for that if you want to get this code to work for yourself. But once we scrape those comments down and have them on our machine, the next step is then to send them off to OpenAI and ask OpenAI to classify the sentiment from -1 to 1 and give us a result. And then we take those results and then eventually we'll plot them. And so if you have no experience with plotting, it really doesn't matter. I'm just going to give you the code to make a nice looking plot, and then we run it. And it takes a while depending on the sample size. I tried one with like 10,000 comments that we were analyzing individually, and it took 2 hours to run. And it also costs like $1.50 or something, or maybe even more. But we'll start small so that we can just get something running together. So I'm not going to write this from scratch, but I am going to walk through the whole process, and I'm going to talk about how we can use TickToken to analyze the cost, or at least the number of tokens that we'll be using up. So that's coming up. All right, so if you want to follow along with this and you want to get this code to run on your machine and tweak it and do your own experiments, aside from having your own OpenAI API key, which of course you'll also need to get a Reddit developer key, or specifically a Reddit client ID and Reddit client secret. And to get these, it's actually kind of buried. It's a little hard to find, but if you have a Reddit account, you can go to this URL, reddit.com/prefs/apps. I'll include a link to this attached to this video. And this will be, the page will look something like this here. It's a very old version of the Reddit UI. And what you'll want to do is go to the very bottom and click Create Another App. And then it will ask you to put in a name, a redirect URI, which will not be used. So put whatever you want there. I guess it probably needs to be a valid formatted URI, but it can be something that doesn't exist. And then you should end up with eventually the client secret here. And then this is not labeled, but this is the client ID. Now I'm going to delete this app entirely. So, I'm showing you this, but this is a throwaway account anyway that I don't plan on using. So once you have those two pieces of information, put them in the .env file under the name Reddit client ID for the client ID and Reddit client secret for the client secret. And then we have the Python Reddit API wrapper package that I'm using. So you'll need to do a pip install praw if you want to use that, right? Pip install praw. And I already have it installed, but again, you'll want to do that. I'm also using some tools for plotting. We'll get to that. If you've never done any plotting in Python, if you've never worked with pandas or Seaborn or Matplotlib, that's a lot to learn. We're not going to go over it, but I'll at least show you what you need to install. Okay, so I'm going to get rid of this because I already have praw installed. So the next step is to figure out what data we're going to be working with. And I've already worked with the city data, so I think I'd actually prefer to try a different example. Maybe we'll work with the European Premier League subreddits. So soccer teams, football teams, Red Devils, Manchester United, Liverpool, Chelsea, Gunners, Spurs. I have a feeling they're going to be the most negative. It doesn't matter if you don't follow any soccer at all, but they're having sort of a rough year in some ways, going through some manager issues. So anyway, Everton as well should have a pretty terrible time. I just picked 8 different teams based off of their subscriber base, the most popular subreddits, as far as the number of people following each one. Okay, and then I'm going to save them in a file name called epltop8.csv. There's no reason really to do this on a single line. I just had a couple different examples I was toggling on and off, so I'm just setting 2 variables. That doesn't do anything. It's just 2 variables. Then we have the code that's actually going to go and collect the comments. And it's a little bit complicated, to be honest. Basically, what I'm doing here is looking to see if there's a file that already exists with the file name, in my case, epltop8.csv. It doesn't exist yet. If it did, we would read it in and try and get data from that file first. And this basically, it's kind of going to cache the results as it goes. And then in case our requests get cut off somehow, our computer shuts off, we close the window, whatever, it can then pick up where it left off. Because if I'm trying to scrape hundreds and hundreds of comments, it can take a decent chunk of time. All right, so the actual logic here, I'm working with pandas, with a panda data frame. This makes it very easy to write to CSV and read from CSV. I don't want to spend too much time looking at the actual logic because it has nothing to do with OpenAI. But basically, we give it a subreddit name, and it's going to go over the posts in that subreddit based upon, in my case, I'm using the .top method to get the top posts in a given month. Now, you could change that and say top posts in a year or all time. I'm doing month because it's a bit more recent. I found that week also worked, but it was very recent. So month was a happy medium, but it's also, by the time you watch this, will not make much sense. The results I get, they could easily be different unless you're watching it the same month that I'm recording this. Okay. So then we have an argument to this function. There's a whole bunch of arguments, but we basically tell it how many comments we're trying to get total from the subreddit. And that's what this logic here is checking to see if we've fetched enough comments yet. Has the number of comments that we fetched been great? Is it greater than the target number that we're trying to get? And if it is, then we just break out of the loop, right? We're done. However, the first time this runs, we won't have any comments. So this is the important logic. For each submission, which is basically a post, for each post in the subreddit of the name, let's say we're looking at the Arsenal subreddit Gunners, .top, filtered by month, so in the top post for that month on that subreddit, we're then going to look at the comments in that post, loop over them for each comment, and there's some logic to see if we already have enough comments. I also have a parameter called max comments per post, because some posts can have thousands of comments, and I didn't want to get all of the comments from one post. If I'm looking for 500 comments per subreddit, I decided it's better to split them across a couple of submissions. So I'll show that parameter. But there's logic here that makes sure that we're not getting too many comments from one post. And then we're going to look at the comment and extract basically the comment body and the submission ID and the subreddit name, and we save those, we write those out to our CSV file. Technically, we're writing it to the data frame, and then at the end, we write that data frame to CSV. If you're not familiar with pandas and working with data frames, it's not at all important. It's just a structure that helps us manipulate and work with data. The other thing that I should mention is that I wrote a little generator here to help me with the comments. If you're not familiar with Python generators, it's also not a big deal, but it takes all the comments that we get from the API wrapper for a given submission, and it filters out the ones that have been deleted or removed and the ones that don't have a comment body, and it returns one comment at a time. It yields one comment at a time. It's a generator. So if you see me using this comment generator down here, that's what's going on. It's right here. For each comment in the comment generator, it just, extracts some of that logic so that we can remove the deleted comments, the removed comments, the ones that aren't actually even comments, and only make sure we're getting one comment at a time that has a comment body. And then we take that comment body and we just store it in a CSV file. We're storing the subreddit name, submission ID, the post ID basically, and then the body of the comment. So let's try running this. Down at the bottom, just the scraping portion, I'll show this. Has nothing to do with OpenAI, remember. That's the next step. So I'm going to save them to a file called EPL top 8, that's file name, and my subreddits, I have 8 subreddits. So I'll scroll down. I'm going to go past all the plotting stuff and the OpenAI stuff to the part where I actually run my code. And the first thing I'm going to do is decide how many comments per subreddit do I want to get. So if I have 8 subreddits, let's just start small. Let's do, because this can take time, I'm going to start small, 50 comments per subreddit, which is a very small sample size, just to be clear. This is not a good enough data set, but it's good enough to show that it works. So I'm going to try and get 50 comments per subreddit, and I want at most 5 or 10 from a given post. So max comments per submission. This is all just going to be passed into my collect comments function I just showed you. And then I can also set a maximum comment length just so I don't get some huge comments where, I'm paying a lot of money to OpenAI to get them analyzed. So this is the line that will go and collect those comments. Let's see if it works for us. Here we go. I'm going to run it, and it says it's processing the subreddit Red Devils, which is the Manchester United subreddit. And it tells us it added 10 rows to our CSV file. And this is going to take a while, even though I'm only doing 50 per subreddit. But I'll just show you, if I look at this file, it should have made me an EPL top 8 file. And here it is. And it will grow as more comments are added. But this is from Manchester United. We can see just our comment text, right? I'll never forget Bruno standing, blah, 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 blah. These are comments from the top posts in the most recent month. Anyway, the comments are in here. If I refresh, we'll probably see some more. Yep. So this is all still Manchester United comments, CSV format. One thing that I'm not doing that I could do is get rid of the empty lines in some comments. Like if somebody leaves a long comment like this, or like this one right here, they often will put returns in the comment just to break it up. I'm putting it in my CSV file. It will be fine. It will be read and parsed, no problem. But it's kind of ugly to look at, and there's no reason. We don't really need those, the proper formatting in the returns, because I'm just trying to get the sentiment for each comment. I don't care about reading it myself. So this will take a little while. I'll end the video and come back when it's done. It's on Liverpool at the moment, and I'll let it keep going. All right, so in the previous video, I started the scraping or the downloading process of the data. It just finished up. So I only got 400 comments. That's fine. I did 50 comments per 8 subreddits. I was trying to do something quick. It took about 3 minutes or so. And you can see a little preview. I returned a data frame. So even though it's writing to a CSV file, we can see the subreddit, for each row, the post that they belong to, the comment itself, and then the score. And the score is not assigned yet. That's going to be the sentiment analysis score that comes back from OpenAI. So in this video, I want to talk about that process. Once we have this CSV file, whether it's 500 comments or 10,000 comments or more than that, how do we use OpenAI to perform the sentiment analysis? The first thing I would say is that there are certainly other libraries I would go to first for sentiment analysis that are cheaper. With that said, this is a fun example, and it works. It's just that it can add up a little bit if we're doing something with hundreds of thousands of requests. So I'm not doing that, but I am going to talk about trying to calculate how much it will cost. So let's start there. The first thing I'll show you is the basic prompt that I've written to score a single comment. I have a function called generate prompt messages. All that this does is it takes in a comment or a piece of text, and it returns a list of comments. So I just moved this into a function because it's kind of long. And it's just a basic prompt that has, our messages format where we have our different roles. So user, specifies a comment. The following is a comment from a user on Reddit. Score it from -1 to 1, where -1 is the most negative, 1 is the most positive. And then I gave it an example. The traffic is quite annoying. And then I give it the corresponding response I expect. Role is assistant. Content is -0.75. I should mention there are different strategies for sentiment analysis. The one we saw earlier was just basically, it's not binary, but it's trinary, whatever you call it when you have three choices, -1, 0, or 1. It's either negative, neutral, or positive. In this case, I decided to go with a sliding scale, a gradient of sentiment, where it goes from -1 to +1, but any value along the way is perfectly fine. So I gave it an example, right? Traffic is quite annoying. It's not fully horribly negative, but it's pretty negative, -0.75. I give it another example, right? This is neutral. The library is downtown. That's neutral, 0.0. And then here's a more positive one. I really love the summertime. Everything is so green. The sun is out all the time. It's a positive 0.8. And then what we do is we have an F string where we give it the same prompt, and then we'll actually add in the comment text itself. So this is just for scoring a single comment. Now, there are optimizations you definitely could make where you could score multiple comments at once. This is just a simple version. It takes one comment, whatever the text is, it puts it in here. And this doesn't make the API call yet or anything like that. This is simply generating our prompt that will then pass through. It generates the list of messages. Okay. The next thing that we'll look at is the function called score sentiment right here. There's a score sentiment singular and score sentiments plural. This is the function that starts the whole chain. It opens up the CSV file, and inside of here, it's going to call our function, which is called score sentiment, for every single comment. But let's just look at score sentiment in isolation. It's quite simple. It has a piece of text you provided in a model. So the comment text, like, I hate living in this place, and then the model, GPT-4 or 3.5 Turbo. And then it calls the generate prompt messages function I just showed you. So that gets a big list of messages that has the comment inserted in it using an F string. And then it just calls openai.chatcompletion.create. We tell it the model, we give it the messages, and then we get the data back. And basically, there's some error handling in here. But at the end of the day, it's going to return a single number, a float, -1 to +1. There is some fancy stuff up here. I'm using a tool called Tenacity. This basically gives me a decorator called retry that gives me some nice logic where I can tell, I can decorate this function that's making a request. And if it fails, I can retry it. There's different ways that I can retry it, how many attempts I want it to stop after. I can set up this random exponential wait, basically a delay, so that I don't get rate limit issues. So it staggers my requests if needed. If it starts to fail because of rate limit issues, I can retry for certain exception types. So there's different exceptions that I'm retrying for. So it just cleans up my code a little bit. It's a pretty popular library. Again, it's called Tenacity. You definitely don't have to use it, but it makes it easier when we're trying to do a bunch of these requests in succession. So this scores a single comment, and then we have the score sentiments function. This is the function that expects a file name, and it expects a model. Whatever that file name is, it's going to read in the data from that file, a CSV file, turn it into a data frame, basically, thanks to pandas. And then the first thing that it does is it calls another function called estimate cost to score comments. And this function uses tick token. So estimate cost to score comments is right here. It's very simple. All that it does is it takes in our data frame and it goes through all of the comments in that data frame. It has a number of tokens. It starts at 0. And it passes through the result of our generated prompt for each comment. Right? We pass each comment through to this function. And this is what's nice about separating out the message logic is I can then test this and I can figure out how many tokens are in the prompt because this function exists in isolation. It's not baked in to the actual request logic. This just makes me the prompt. And then we can do this for every comment. So I'll pass in each comment. I'll get this big messages array or list back. And then we can use that function that we learned about a couple videos ago, num tokens from messages. It will tell us how many tokens are in that list of messages. And we basically repeat that over and over and over. And we do that for every comment in the CSV file right here. And then I have some cost estimation here. This is based on using GPT 3.5 Turbo, and it may change, but GPT 3.5 Turbo is $0.002 per 1,000 tokens. So we count up all the tokens and all the prompting and all the messages that are required to do every single comment in our CSV file. And then we take that number of tokens we get back from our function, num tokens from messages, and we multiply that by the cost. All right. So that happens first. I mean, technically it'd be nice if we just had like a little input where you had to hit enter or type Y or something to proceed. Because right now it just tells you what it's going to cost and then it just goes on with it. You can always exit out anyway. And then once we've done the cost estimation, we then are going to go over every record. So right here, what we're doing is taking our data frame, turning it into a dictionary, saving in a variable called record. So this will be a dictionary basically that has all of the data from the CSV file. And then for each element in there, we loop over it. We take the comment ID and the comment. That's the actual text of the comment. And we're going to pass that through to score sentiment. So score sentiment will get the body of the comment and then the model. We accept an error. Sometimes there are certain comments that are unscorable. So we just try a couple times and we accept it and just basically ignore it if it doesn't work. And then I'm printing out just some stuff that says, how many comments have been analyzed, the body of the comment and the score, just so you can see it. And then finally, we write everything back to CSV. So we're working with a data frame. We turn it into a dictionary. It's kind of confusing. Then we take that dictionary, turn it back to a data frame, take that data frame and export it or save it to CSV. It has nothing to do with OpenAI. Now remember, the core logic of actually requesting the chat API is happening up here in our score sentiment function. That's where the OpenAI.chat completion comes in. This function just serves to call our cost estimation, to import the data from a CSV file, and then to actually call the individual score sentiment function over and over and over. So let's see how this goes. You already saw the prompt. It's pretty straightforward. I gave it some examples. Let's try it out with our data down here. So I've collected the comments. The next step is to score these sentiments. And I already have my variable called file name. And it tells me it will cost approximately 20 cents. Now this doesn't actually take into account the response tokens that we get back, but it's fine because it's just going to be a single number that we get back. It's a small number of tokens, so it's not entirely accurate. It's just counting the prompt tokens. Now you can see it's going, and sometimes it may get hung up, and that's where our retry logic comes in. So let's take a look at an example. Like this is a comment right here. He looks fitter now than he did in the 90s, whoever that's about. And it got a score of 0.6. So pretty positive, but not like astoundingly positive. Here's a very negative one. I'd be embarrassed to have him on my team. It's a negative 0.9. There is some bad language in here, by the way, so I apologize for that. It's coming from Reddit comments. So you can see we're getting results, pathetic from Luke Shaw, negative 0.9, or pathetic from Shaw. It's working. We're at least getting some results. And it takes a little bit, but it's not that bad. Let's see, we're already 25% of the way done or so. Yeah. So I'm going to let this finish, and that's pretty much all there is for the OpenAI portion of this. Once we get our data back, it's going to be saved into that same CSV file, but now it will include a score, a sentiment score. And I didn't really show that logic. I wanted to focus on just a high-level overview because I don't know how much you actually care about the code itself compared to the OpenAI side of things, which is pretty straightforward here. It's just a basic prompt that I've extracted into its own function that returns a bunch of messages, and then a function that calls OpenAI.chat completion. Simple enough. The logic to work with CSV and data frames and dictionaries and all of that is a bit more complex. So if you have questions, you can definitely take a look at the code, download it, and I'll give you the CSV file so you don't have to actually do the analysis yourself and pay the 20 cents or so that it costs. Anyway, you can then ask questions in the discussion forum if you do have any about the implementation here. So I'll be back when this finishes up. Okay, that finished up. It shows me a little output that just says scoring completed, right? So we don't really need this output, but it helps just so you know what's happening. And the final step is to plot things. Now this has nothing to do with OpenAI, but now our data set looks like this. If I refresh, here we are. We have a CSV file that has, the ID of the comment, the subreddit, the submission that it belongs to, the post, and then it now has a score. So we're going to take all of those scores and plot them. And I'm not going to do a whole introduction to plotting, but basically, first of all, I have a course on that if you're interested in learning more about things like pandas and matplotlib and Seaborn. There's the plot sentiments function that's most important. This is what goes through and actually creates the plot. So it expects a data frame. There's some styles that we're setting using Seaborn, the color of the axes, and then we're getting the two things out of the data frame, the score and the subreddit, because that's what I care about. I don't care about the individual commenters. I just want to know the overall scores for each subreddit, all of the comments belonging to the Come On You Spurs subreddit or the Gunners subreddit or the Chelsea FC subreddit. And then we plot them using a KDE plot, and there's there's a bunch of parameters that we set. Again, doesn't really matter if you're familiar with it or not. Then we label the axes, and why don't I just show you that it works or that it doesn't work? Let's see. There is a function as well here to sort them. So we sort them by the average positivity or negativity. So I'm going to run this down here. It's called plot sentiments. It gives me some warnings about running out of tight space. I mean, I could make this prompt a bit bigger or the plot a bit bigger, but here we are. This is our result. And as I mentioned, I expected the COYS, Come On You Spurs subreddit to be the most negative. They're not actually the worst performing team if you don't know anything about the Premier League this season. They're just kind of a long time, I don't want to offend anyone, a running joke is that they're bad. And there's a lot of pessimism about the team in recent months and that they should be performing better and that their best star is going to leave the team in the future. And anyway, you can see clearly they are far and away the most negative subreddit. And this is a very small sample set. Let's be clear. It's only 50 comments per subreddit. Not enough to draw any real conclusions. Then we have Chelsea and Liverpool, two teams that are drastically underperforming this year. Newcastle is an interesting one. They are overperforming what people expected. So there's a decent chunk of positivity, not a lot of neutral sentiment there, and then a decent chunk of negativity. And then the most positive is Gunners. Arsenal, which happens to be the team that I like, has been having a really good year and has been leading the table basically for the, last 6 months or something. And there's a lot of positivity there. So like I said, we're not gonna draw any real conclusions from this, but it's kind of a fun experiment, and it's also just a good use case to show you, cost estimating and using tick token and the benefit of taking that function that we didn't write, by the way, it came straight from the docs. That takes returns a number of tokens based on a messages list. Well, we use that here, and by extracting my logic to generate the messages list into a standalone function, then I can test it using tick token separately from the logic to actually make the request to OpenAI. So that's it for this demo. Again, we didn't write anything. I just gave you the code and showed it to you. And I'm sure it's a little overwhelming, but I just wanted to show an example of something involving tick token and involving, a bunch of requests being made and some estimations. So if you're not familiar with the Premier League, if you don't care at all about soccer, football, whatever you want to call it, you can try the cities dataset. I've provided that CSV file as well in our code if you want to use that one, or come up with your own experimental dataset. Find subreddits that make sense. So I tried cities, iPhone versus Android, Star Trek versus Star Wars. If there's different fandoms or some different group of subreddits, maybe politically different aligned subreddits, conservative versus liberal subreddits versus the moderate subreddits versus the default politics subreddit, different TV shows and the way their fans talk about them, stocks and companies and startups. I'm sure there's things you could come up with. That's pretty much it though. So simple enough, right? The complex logic really comes from doing the scraping or the downloading of the data. And then the actual prompting is straightforward. It looks bloated just because we have some examples in here, right? Showing it the format that we want. But then if you ignore all this stuff around retrying and adding this weight random exponential multiplier, all this stuff, and the different exceptions that we'll retry on, if you ignore that, it's a very simple call. We're just calling it and extracting a number out with a regular expression, turning it into a float and returning that. And then we do that over and over and over and over and save that to a CSV file for all of the data that we get back from Reddit. We run each comment through our function that gives it a sentiment score. And then there's the plotting logic, which, if you're not familiar with that, I didn't really go over it. It's a lot, and it's a lot to cover, but it works. That's all you need to care about. It takes a data frame and it will plot it. And that's what we see here. Okay.